Hi everyone. Today I'm going to talk about the problems that deep learning researchers face. But I would like to start my slide with this question, my presentation with this question. Why deep learning is so efficient? If you put unreasonable effectiveness of deep learning in Google Scholar, you would have more than 6,000 articles that are relating to this topic in this way or another. But we know from practice, from experience, that if we want to build a neural network-based system, what do? Yes, absolutely correct. We add more layers and more data, and everything starts to work greatly. The quality and the precision of the model improves, and the obvious trend that we have seen in the recent years is that more and more models appear, and they deliver higher and higher quality. It is true in the last several decades, many neural network architectures were made, and thanks to the stochastic gradient descent, in the majority of the cases, we see that the more data we add, the better the quality. The more layers you add to the model, the better. And whatever crazy and complex architecture you create, you see all this zoo of activation functions, decoders, encoders, recurrent networks, self-attention, and so on and so forth. They still converge. At the same time, the deep neural network helps to solve problems not in one domain, specific domain, like speech recognition, but in many other domains, like computer vision, natural language processing, reinforcement learning. All that leads us to the question, are there any problems at all in this area? And maybe it will go on like that. We'll just pour in the compute resources and get even better results. Well, that trend is going to continue, obviously, but more and more researchers start to look at some conceptual problems that algorithms of deep neural networks face, and if we can answer these challenges, respond to these challenges, we might increase and improve dramatically the quality and speed of our algorithms. Let's go through a set of problems seen in this field. Obviously, this list is not exhaustive. Many researchers have their own lists of problems, but there are problems that are kind of set for this area. The first problem is that some class of algorithms need a lot of data, need to collect data. Data sets have to be balanced, and there are other requirements, and that means a lot of resources for the collection. And that generates the second problem. To train the algorithms, you need to make a lot of steps. And since you are making all these training steps, you need more time, therefore, and therefore you need more compute and more energy. And this is obviously one of the pain points of the current deep neural networks. The other problem is the possibility of generalize the knowledge received and ensured by the model. How can we resolve the same tasks? Can we use the same algorithm, or can we reuse or recycle some part of the knowledge that we have received to use in previous models? That's another thing. Another problem that not many people talk about, although it is a big showstopper in terms of development of our algorithms, we're talking about limited input size. Yeah, that's true. If we have a simple model, and if it's convolutional networks or transformer networks or any other FNN, we see that if we want to see the sequence, we need to put all the sequence in the model. And in case of the transformer, when we have a dependency from the level of the elements, we cannot just grow the sequence. We we have to think about some of the barriers, some of the workarounds to resolve this problem. We need to put these algorithms and put them in the past, so to speak. We use back propagation through time to train them, and the gradients, these gradients steps to the past means that we train recurrent network as an FFNN with the depth that is equal to the number of steps to which we pulled back our previous network. So that means that if there are some events between which there is a connection and that influence each other, if the gap between them is larger than the length of the sequence that we can give to the algorithms, we can't do that. The current backpropagation algorithms will not be able to find the dependencies between these two events. The other problem many researchers highlight is related to the following. Despite the fact that the models can predict the sequences, they are limited in terms of the reasoning. So these sequences might be garbage or might be not filtered with the logical output rules. So the neural network architectures are bad at modeling the reasoning function. The other problem related to retraining the deep neural network model is the catastrophic forgetting problem. So if we take a model that used some set of data to be trained, and if we start to use a slightly different set of data, it is very quickly that our model forgets the previous tasks, and when we try to use it to resolve the previous task that it used a lot of time to train for, it cannot do that. And this limitation puts a barrier between building the system with continuous learning. We would love to have a system who would be retraining friendly. You know, it's like a pupil in the school. They learn new things every year without forgetting the stuff he or she learned before. To resolve that problem, we need to understand how to respond to catastrophic forgetting. Another problem for the neural network-based systems, if we talk about generative models for natural languages, and here we're talking about the goal setting. If we want not only to generate some possible sequence, if we want to put the text, new text in some certain style, or if we want to build some story, we need to create the goal based on which the sequence will be generated. And obviously, when we talk about these algorithms, this problem is not been resolved. And if we talk about reinforcement learnings, we often put the awards, but this award function should be decomposed by sub-goals, and the goal of the task of decomposing our major goal in sub-goals is very far from being resolved. Another very important problem related to the reasoning is a common sense problem.
For example, it is very vividly manifested in cases where we want to use end-to-end neural networks to build dialogue agents. Because in a dialogue, common sense plays a very important role, because when people communicate with each other, we assume that the other person also has knowledge about the world around us, similar to the knowledge that we have. And we don't have to describe the situation in full detail. Instead, we just make a reference, because we assume that the person will understand it based on the context and the common sense. This common sense is a trap for dialogue agents, because they are very often narrowly specialized, and they know this narrow area very well, but if you step beyond it, they don't know the bigger context, they find it difficult to navigate the dialogue, and the dialogue stops being effective. And the last problem I want to talk about today is the explainability of artificial intelligence. Deep learning models, neural networks, they are not very strong in terms of explainability, and the model is often struggling to explain why it made this or that decision, and that would be valuable for us to understand better how they work, why they work this way, and this is also important for building trust with customers. So these are the problems that exist today, and now let's look at some of these solutions that we're trying to develop, or that we have already developed, at least partially, for the problems that I listed. Of course, I won't probably have enough time for all the solutions, because then I'd have to make a whole university training course about this, but I can highlight just some of them, some of the examples. Let's look at the first two problems: large data sets and many training steps. Over the last 2 to 3 years, we have clearly been observing a revolution of sorts. At first, it was in natural language processing. Now it's also in computer vision. This is evolution based on gigantic self-supervised models. When we got a transformer-based architecture, it turned out that we can pre-train a model, and then this pre-trained model can be used for other tasks. So on one hand, we can easily fine-tune the model for a different task, and then we'll need much less data for a good solution. So this way we tackle the first problem, the large data sets that are required, or we can even do without the training. In the first case, we had to use the gradient descent. So we can do without it, without the training. We use the zero-shot training, so to speak. Let's look at it as used in GPT-3, the language model that was trained to predict the next word in a sequence, and it was trained using big corpora of natural languages derived from the internet. So zero-shot is where you train a model without any specific additional training. So for example, we have a sequence. Translate from English into French, cheese and arrow, and we expect the model to immediately generate the answer, the translation. It turns out that the biggest model, 175 billion parameters, it has roughly 10% accuracy in solving this problem, translation from English into French, as defined above. If we go from zero-shot to one-shot, where we have one correct example of one correct answer as an example for our model to train, in this case, we will see that the accuracy will grow from 10 to roughly 45% for the large model, and this is a big leap forward. And if we give our model even more examples of an answer for training, the accuracy, the quality of prediction gets even better. The more parameters we feed into the model, the more accurate is the answer. But this generalization, this transposition of knowledge from pre-trained model to the ultimate task, it is currently possible not even within the text domain, but between the text domain and the visual domain. So, for example, we can look up a lot of images online with captions. We can feed it into our transformer, and we will have the first part of the sequence being words and the other half being images. So we want our model to predict the image based on the textual description. We put in the description of an image, and the model generates the output. The source images are taken from OpenAI, from their model. This model was not made openly available, as Bear Devices trained the same model for the Russian language, and it is available publicly. It's an open source model, so you can check it out and experiment with it. Great license terms. We can also try to transfer knowledge between domains using contrastive pre-training. That is where we take the encoder of text and image, and we build this common space of representations that will contrast the text and images. And so, if the image is not related to the textual description, it will not be united. It will not be converged. So these are very interesting systems where we don't have to use additional training, additional classification. We can simply use the natural language description of the image that we want the model to generate, and then using cosinus range, we can apply the ranging of the output. We can use the system to range, to sort, to search, and also to train. For example, image generation using style GANs, a lot of different capabilities. Okay, let's look at the progress in solving the problem of problem-solving training. Seemingly, the biggest progress was made with deep reinforcement learning. This slide illustrates the way algorithms, AlphaZero algorithm, has been mutating. AlphaZero, developed by DeepMind for playing the game of Go. It is a convolutional neural network-based algorithm, and also an algorithm based on the stochastic tree search. We saw that within a span of several years, this algorithm mastered the knowledge of the game, deep expertise. This deep reinforcement learning, as it seems, can help us create more and more universal algorithms that can be trained in different domains. And this is why they're universal. But they are still struggling with transferring knowledge from one domain to another. And the last example I wanted to provide regarding the problems, the problem of limited input. This is where I wanted to talk a little bit about the model that we are working on at our institute, memory-based learning in neural networks, and specifically the algorithm of memory based on uncertainty of events. The problem is that in order to train the model to identify correlations between events remoted in time, we need to use gradients. If we cannot do it, we need to find a way to work around it. And Artem Sorokin, one of our team members, he came up with this interesting model where we can first run an exploration of the environment. We identify the events in the environment which are the most uncertain for the standard model, and then we take these events specifically and we train the predictive memory based on these events in order to predict the attributes that can reduce the uncertainty of these events the best. Training here does not really require big gradients, and it can be implemented using, for instance, a gradient in a recurrent neural network with only one step backwards. This means that we can identify interrelations across a very big span of time. We tested this algorithm on a set of tasks. On the left-hand side, you see the simple example where we have a task in the T-labyrinth environment, and the algorithm gets hints about where to turn, left or right, to get the reward. And on the right-hand side, we see an example of standard scenarios of training. Even if we apply the gradient for the length of the corridor, they cannot really navigate it. In our case, with pre-training of the memory module, the model can navigate and can work, and can also work even in the environment of noise. Here on the right side graph is where we add hindrances, obstacles. And it turns out that even in this case, the algorithm enables us to filter and identify the uncertainty events, the precise uncertainty events that are relevant and important for problem solving. There is a dependency. The more we train the memory, the better our algorithm is at identifying these sequences that are remote from each other over a big span of time. Now let's try to paint a bigger picture and get a clearer understanding of what we have at the moment. What is our landscape of AI problems? What are the neural network components? What are the approaches that we need to be developing in order to solve the problems that haven't been solved yet? Clearly, with the problems of big data sets and many training steps, for these problems we can already use computer vision models and self-supervised learning. When it comes to common sense problem, explainability and reasoning, to solve these problems, we need algorithms that would ensure planning and some sort of simulation of an outer world. We also need to work out models of skills and actions in order to ensure the explainability of an AI model, in order to solve the problem of a limited input size. We need to add working memory to our model so that the model can remember potentially important events. To generate goals, we need to be able to determine the goals appropriately and decompose these goals. This is also an important component in our model. Also, episodic memory is essential, because if we're building intelligent agents that are constantly accumulating experience, they need to remember what happened before. If we take a bird's eye view of the situation, we will see that some of the models can be attributed to the outer world models. On the other hand, there is certain agency. We use this outer world model to solve specific tasks. And in this framework, we also need a component that would ensure the model of the agent itself within this world. This is the way the agent envisages itself in the world and predicts its own actions. Learning, this is something that has an impact on the perception of the world and the agency. The world model and agency, one of the key components here is exploration. This is needed for developing the ability to train and accumulate knowledge. Novelty detection, clearly. How do we know that at this point we need to learn something new, our solution does not work? Modularity and hierarchy, this is needed for planning, so that we don't forget what we've learned. What's interesting is that all these circles can be divided into... Some of these components initially were within the domain of neural networks, distributed representations. The right part of it, the components related to agency, those were in the focus of attention over the last 10 years, related to AGI and searching for it. So we can observe this evolution where we use neural networks to try to solve problems which previously were only available to AGI. So these are our two approaches, two opposing approaches, neural AI and symbolic AI. We see new areas emerge, deep RL, for example, that combine elements of the two approaches. Then there are more complex tasks like mu0 using some of the components from symbolic AI and neural AI, models for generating knowledge graphs based on transformers. They use pre-trained models, and they use knowledge graphs to generate predictions. And I think it's clear that we will see more and more models which combine these approaches from neural networks and symbolic AI. And essentially, I think we can talk about a synthesis of neural and symbolic AI, neuro-symbolic AI, where neural networks will be approximating symbolic approaches and symbolic approaches will be beneficial for neural approaches. How does our institute, Artificial Intelligence Research Institute, how do we address these problems with the projects we're developing? The core AI projects, one of them is weekly supervised learning for NLP. This project tackles the problem of many training steps, big data sets, limits of multilingual and NLP, similar problems, similar areas, effective multi-model, multitask models, self-supervised learning, multimodality, big data sets, once again, generalization, next, neural symbolic integration in learning and planning. The projects that are related to this new synthesis stream, this is where we have planning, goal setting, skills, modular representation, and we try to tackle many problems at once. Synergy reinforcement learning, once again, a very synergetic project, so to speak, that addresses a lot of problems of modern deep learning. Working memory project, the one I touched upon already, training long sequences, and last but not least, the project on automated theorem proving. This is about reasoning and modular representation. And in conclusion, a couple of words about the long-term roadmap of our fundamental research at the Institute. We have the three core groups: world, model, agency, and learning. And in these areas, we will be trying to identify the key problem components and combine them in order to, maybe in the next few years, get closer to solving the problem of common sense, and then maybe a bit later, on the, say, dozens of years horizon, we will be able to probably work out solutions to help scientists solve the problems of society every day. Thank you for your attention. I'll be happy to answer any questions you have. Thank you very much, Mikhail. Thank you for joining us. Unfortunately, we do not have time for the Q&A, but I'm sure next time we will have questions for sure, and I hope we will have time. I hope to see you back.